Right. So last day we learned a little bit about Stern-Gerlach apparatus and vector spaces, and like we learned about vector spaces in a very informal way. So in the first few minutes, let's recap what we have done till now. So we looked at the Stern-Gerlach apparatus, and in which we had a beam of silver atoms, which were directed to a Stern-Gerlach box, which we have shown here. Inside the box, there was some inhomogeneous magnetic field, and because of that, because of the inhomogeneous field, the particles having different spins got separated. So the spin up particles, so if the Stern-Gerlach apparatus is in some n-roof direction, n-hat direction, then we get two spots on the screen of the Stern-Gerlach, and the upper one corresponds to the up spin in the n direction, and the lower one corresponds to the down spin in the n direction. So what we concluded from this experiment is that since we got only two spots on the screen, that the spin angular momentum is a quantized quantity, and that Stern-Gerlach apparatus oriented along some direction in roof in the real space measures the corresponding component of the spin angular momentum of the electrons. Now, last day we talked about Stern-Gerlach apparatus in terms of silver atoms. So, but really, it was only the unpaired electron in the 5s orbital of the silver atom, which was leading to all this phenomena. So can get exactly equivalent results if we used a beam of electrons instead of a beam of silver atoms. And since the electron is the spin of the electron is what is making the difference, from now on we will talk about the Stern-Gerlach apparatus in terms of electrons only for the sake of simplicity, because the other degrees of freedom of the silver atoms are not really coming into play here. And last day also, what we tried to see what happens if we combine different Stern-Gerlach apparatuses in the same or different orientations together. So we took Stern-Gerlach apparatus and we cascaded two Stern-Gerlach apparatuses in Z direction. So the output of the first apparatus, of course, contained both up Z and down Z spins, because the oven which was creating the silver atoms or the electrons, they were randomly oriented. So we got 50% of both. We stopped the down spins from going ahead, and that up spins we fed into another Stern-Gerlach box in the same Z direction. And of course, since we were giving only the up Z spins and through another Stern-Gerlach in the same direction, we got only the up spin particles at the up spin electrons, let's say, at the output, and we didn't get anything in the down Z port. And when now compared to this, in contrast to this, when we introduced a Stern-Gerlach apparatus oriented along the X direction in between the two Stern-Gerlach apparatus in the Z direction, what we found is that instead of one output, like only the up Z output, we were getting both up Z and down Z outputs from the last Stern-Gerlach apparatus. And this was a little bit counterintuitive, because what we would expect is that since we are sending in only the Z particles, no matter what we measure, even if we measure the projection along the X hat direction, as I said, SGN measures the SN component. So even if we measured the SX component, the SZ component should not have changed. And so we should have got only up Z at the output of the third Stern-Gerlach apparatus, but we find that that is not the case. We find both the outputs. So this was this was something which classical mechanics could not really explain well, and so this is one of the motivation, this experiment and this incompatibility with classical mechanics uh, is inspiration for finding a more general theory which will explain this phenomena as well. And in order to, that theory, of course, is quantum mechanics. And we argued that in quantum mechanics, the state will be given by some vector in some abstract vector space. And we very informally discussed the concept of vector spaces as a generalization of the real space R3. And we talked about R4, R5, Rn, and C2. And we learned that the generalization of dot product is the inner product, and the generalization of length is the norm. Okay. Uh, with that introduction, recap rather. I'll ask you if you have any doubts regarding this part, then we can discuss and then move on.
Hello.
Hello, yes.
Uh, I want to ask you about material reference book. Which reference you for this?
Mhm. Uh, can you please repeat?
Which reference book you I can read for this?
Okay, a reference book. Okay. That's a good question. So the reference books, I would recommend you can study these things from whatever I'm talking about, from R. Shankar, uh, Principles of Quantum Mechanics, and eventually we would move to Nielsen and Schwang, the book on quantum computation that they have. So for the time being, I think R. Shankar should be good enough. Is that okay?
Okay, thank you.
Hmm. Okay. And name of the book by Nielsen and Schwang is Quantum Computation and Quantum Information. Okay. Is there anything else? Okay, if not, let's start with today's session. And what we will do today is um, a formal definition of vector space. So last day we defined vector spaces. We talked about vector spaces, but not very rigorously. Today we will do that. Okay. So the definition, formal definition, is that a vector space is a subset V, and and it is said to be defined on the field F just F. And if the following conditions are satisfied, so if for all elements, let's use a different color. So UVW belonging to V, and ABC belonging to F. So the elements of the V, which will form the vector space, they are said to be vectors. And the elements of the field are what we will call scalars. So so the field is a field of scalars, we can say. And we will not go into the like formal definition of a field. For our purposes, we will just assume that field is a set which contains scalars, and that's it. So so we will call it a vector space if it satisfies the following properties. So firstly, um, so we will if you take a linear combination of say u and v, which means you take the vector u, you take the vector v, you multiply with two scalars, say a and b, and you add them. So this is called linear combination, as we had discussed last class as well. So if if on taking the linear combination, that element is also a part of the same vector space, then this condition is called closure condition. Closure and under linear combination. And this is the first criterion for our vector space to be a vector space, for the set V to be the vector space. And there are several other criterions. So you can in order to relate, so you can take the example of real space again. So let's say these are two position vectors, r1 vector, r2 vector, and then if you take if the field is say the field of real numbers, then if you take two real numbers and multiply with those vectors and add them, you will again get another vector in the set of real numbers on in the space of real numbers only. So what I'm trying to say is that if you say, let's say V is R3, then let's say U is R1 vector and V is R2 vector. And let's say the F is R. In that case, A is some number, say 2, B is some number, say 3 real numbers. And if you just take A U plus B V, then what we will get is that some 2 R1 vector plus 3 R2 vector, which will again be a vector in the real space. So this is one condition that has to be satisfied by the vectors, by any element of the vector space and elements of the corresponding field. Now, the second condition that we will come to again relates to the vectors only. So if you have two vectors like u and v, so u plus v should be equal to v plus u. And this is referred to as commutativity. So commutation under vector addition, or is basically the commutative property. So the order does not matter. That's what commutative means. So commutativity of vector addition. And so again, if we take the example of R3, then R1 vector plus R2 vector and R2 vector plus R1 vector are basically the same. Okay, so the third property is associativity. So let's say you take v plus w addition and then add it with u, or you take the addition of u plus v first and then add it with w. Both will be the same, and this condition is known as associativity. Now, again, if we want to take an example of, say, the real space, then R1, R2. So let's say you add R2 and R3 first, add it to R1, or you add R1 and R2 first, and then add to R3, they would be the same. And notice that these commutation, associativity, so these follow from the commutation and associativity of real numbers themselves. So if you remember, like R1 vector is nothing but a tuple of real numbers, right? So X, Y, Z, something like that. So since the individual elements are commuting under addition, so the real numbers are commuting and associative under addition, the entire vector which is formed out of this commute is commutative under addition and associative under addition. And the fourth condition, sorry, also relates to the vectors only, and they say that there should exist a null vector, and we will denote it by, let's say, theta. And yeah, theta belongs to the vector space, which will, the null vector will also be a part of the vector space, uh, such that u plus theta. So u, v, w, as we had defined before, these are elements of the vector space only, or of the set V only. And so u plus theta, so if you add the null element to theta, it will remain the same, and it will be the same as theta plus u. And if you think about R3 here, then the null element is nothing but the origin. So 0, 0, 0 for R3. And uh, for the fifth condition is that for every u belongs to V, there exists, sorry, W, which is also a member of the set V, such that u plus w equal to theta. That is, if you have some vector, say in, again, if we take the example of R3, so let's say you have a vector which is R1 vector. So there is always a w which is minus R1 vector, so that when you add these two, you get theta, the null vector. So basically u plus w, and the null vector here is origin, so 0, 0, 0. Yeah, and now going on to the sixth condition. So it says a plus b. So notice that a and b are scalars. They are members of the set F, the field. And if you add a plus b and then multiply it with v, then what we get is a times v plus b times So basically you can bring the V inside this summation. And this property is called, so basically this, what this property tells us is that scalar multiplication is distributive in the scalars. Hello, is anybody speaking? Uh, if you have any question, you can speak up, or I would request you to mute yourself. Is introducing some noise. Okay, so what this means is that uh, the vector V is getting distributed over this scalar addition. So A plus B was addition of scalars, that is, and scalars, remember, are the elements of the field. So the vector, when we are multiplying the scalar addition with the vector, then individually the scalars get added to the vector, and we have this. So basically it's getting distributed over the scalars. And analogously, we can have the a corresponding thing for the distribution of scalars into vectors. And that would look something like A times V plus W equal to, and that would be A V plus A W. Sorry. So again, okay, I forgot to give the example for in R3 for the last one. So let's say something like 2 plus 3, which are scalars, times R1 vector. So it would be 2R1 vector plus 3R1 vector. So this is what this property says. And here, this means that scalar multiplication is distributive in the vectors. And a similar example you can think about in for the real space. So say 2R1 vector plus R2 vector is 2R1 vector plus 2R2 vector. So this is what it says. And now, if you say multiply a scalar with the vector, and then you take that multiplication and multiply it with another scalar A. So let me maybe write it. Uh, hmm. So that is equivalent to multiplying the scalars first and then multiplying with the vector. And this is said to be the associativity of scalar multiplication, because it doesn't matter whether we multiply the scalar to the vector first or multiply the scalars first. And this is analogous to the associativity of vector addition, if you think about it, because here also there were three elements. We were performing an operation on the first two, so one pair of elements first, and then adding that to the second, and then a different pair of elements first, and then adding that to it. So here also it's a similar thing, but with multiplication. So anything which corresponds to a situation where there are three elements and we are playing with the order in which they are operated, then it is said to be associativity. And at this point, if you're feeling bored or sleepy, I don't blame you. Just bear with me for a while, okay? So we'll get to the good parts. And the final, or rather, okay, I think I have sort of messed up my color notations. So what I'm trying to do is represent all the scalars by blue and all the vectors by red. Okay, and the final condition that it has to satisfy is that 1 into the vector should give me the vector again, where, oh, again, where 1 is the unit scalar in F. And okay, and that means that, and what does it mean by unit scalar? That means 1 times any scalar is the scalar itself. Yeah, so where this is in the field. So these are, so if we have to officially define a vector space, this is how you define it. Now notice that, okay, I haven't again given example for the last two. Maybe I should do that. So yeah, so now if you take, say, 2 times 3 into R1 vector, that is the same as doing 6 times R1 vector. Basically, you multiply 2 and 3 first and then multiply it with the vector. And 1 into R1 vector will be R1 vector, where this R1, R2, these are all elements of R3 as we had assumed, and these are of course real numbers. Now, you might say that, okay, why are we writing these rules? These are very trivial. So that vectors will be commutative, associative. These are very trivial. Yeah, you are saying that because you are mostly familiar with real spaces, or I mean, those of you are starting out. But there might be structures where commutativity, associativity, these are not so obvious properties. So that's why we have to lay down some rules that when will we call some set a vector space, or when we will not call it a vector space. Okay, so these are the rules, and as you can see that the real vectors, the real space vectors satisfy these conditions. And so anything else, any other set V on some set of scalars F will also, which satisfies all these conditions, we will also call them a vector, or we'll call that set V a vector space. Now, so last day we argued that the C2 is a vector space, as in we argued that it is a generalization of R3. Now, having written down these conditions, I would ask you to check if this C2 is really a vector space over over C. Okay. Achha, okay. So basically here C is the field and C2 is the vector space. So here you have to check whether all these conditions that we have, all the 9 conditions that we have listed down, if they hold true for this C2 over C. So this is something which you can do in your leisure time. But for the time being, let's um, ask ourselves whether R3, the space that we know is a vector space, but is it a vector space over C? So if I consider my field set of scalars or my field to be the complex numbers, then is R3 a vector space? So can somebody enlighten me?
I think closure under multiplication is defeated because you can multiply by I and take the vector out of R, right?
Exactly. Yes. So let's say we have, you're absolutely right. So let me just write it down for you. So let's say there are two vectors. You have taken R1 vector, which is something like, say, x1, y1, z1. And you have taken another vector, which is x2, y2, z2. And so now notice that since my field is scalars, I can take some a equal to say 3i or something, which is a complex number, or a b equal to 4i plus 6, something like that. So if I take this and if I try to find a r1 vector plus b r2 vector, then you'll see that this entire thing, this will now become a complex number. Or rather, it would be something like C3, but it will not be a part of the real space because the individual elements will no longer remain real. So, okay, let me calculate it explicitly for you maybe. So maybe something like 3ix1 plus something. Okay, let's take a simpler example. Let's say it is 6, then it would be like 6x2 uh, hmm, and some 3i y1 plus 6y2 and 3i z1 plus 6z2. Now see x1, y1, z1, x2, y2, z2. These are all real numbers. So 6x2 plus 3i x1 will be a complex number. So this will not be a real number. So we can say that this triplet would not be a part of the real space. So the closure condition is violated. So the answer to the question is R3 a vector space over C is no. But is R3 a vector space over R? Most certainly, yes. And so we knew that R3 is a vector space. But when we are defining vector spaces, so what I'm trying to say is that we have to be careful about what field we are defining with the vector space. So it's not just sufficient to say that R3 is a vector space. You have to mention that R3 is a vector space over which scalar field or over which field. So for example, R3 is a vector space over R, but R3 is not a vector space over the set of complex numbers. Okay, so and this was the closure condition, if you remember that under linear combination, this should be closed. It would AU plus BV should belong to the same set, and that condition is getting violated here. So as somebody pointed out, so closure is violated. Okay. Now, okay, let's look at a few more examples, maybe. Acha, now one thing that, yeah, so let's look at another question, which is R a vector space over R? So basically here the vector space is also the set of real numbers and the scalar is also a set of real numbers. So will this be a vector space? This is an open question, so anybody can feel free to answer. If you want, you can also answer in the Zoom chat. I can also see that.
I think any set is a vector space over itself. I might be wrong, but I guess
Yeah, I think, yeah, you are absolutely right. Provided that the set is also a field. Okay, and acha, before I move on, I must inform you that fields also, like, we can't say that any set is a field. So fields also follow certain rules. And if you want to learn more about what fields are, then I would refer you to the book by S.K. Mapa. I think the name is Higher Algebra, Linear and Abstract. I, I think this is the name. So you can like look at what are the conditions one has to fulfill in order to be a field or basically a scalar. So as long as the field, as the set satisfies those properties, then you are absolutely right that any set, any field is a vector space over itself. Now, but one thing you might find confusing here, especially those of who are just starting out, is that how is the vector and the scalar belonging to the same set? So, so let's say what is R? R is basically the number line, right? So you say you talk about a vector here, so it would be something like, say, so the unit vector would be x roof. It would be something like 1.5 times x roof. Another vector, let's say, we talk about another vector minus 1.5 times x roof. Now, the thing is that, and this is, say, the origin. The thing is that since there is only one dimension involved, and there's only one unit vector, let's say, that's why this x roof or the denoting the direction is sort of redundant. As in, we could also just denote these points by numbers, right? So like point minus 0.5, 0 and 1 and 1.5 all correspond, and they would be totally equivalent. So you can write x roof if you want, you can avoid it if you want. So what I'm trying to get at is a one-dimensional vector can be treated as a scalar and vice versa. So basically, one-dimensional, scalar can always be treated as a one-dimensional vector. So okay, with this, let's move on to the next example. So is Q, and where Q is the set of rational numbers, a vector space over R. So yeah, maybe I'll give you a couple of minutes to think about it. And
I think it is yes.
okay, okay.
Because if a field is, hang on, let me try to get it right. Okay, so if a field is a vector space over itself, then that should be true for any of its subset also, right?
Okay, let's see. Okay, let's try to see whether all the conditions are fulfilled. Okay. Let's start with let's say the condition of closure. So that is the first condition that we got to check. Now, let's assume two rational numbers. Let's say UV belongs to Q. And let's assume two real numbers. Let's say A and B, which are real numbers. Now, notice that real numbers can also be irrational. Okay, so now we have to check whether AU plus BV, whether this is also a rational number or not in general. Okay, so that is what we have to check. Now let's take a example. So let us take two rational numbers, say U2, V3. So these are rational numbers. And let's take two real numbers. So as I said, real numbers can be rational. So let's say A equal to √2 and B equal to 3, because they can be rational as well. Like real numbers can both irrational and rational. So why not? So what will, in this case, what will this be? So this will be √2 into U. So 2 √2 plus 9. Now, is this a rational number? So in case you are a little rusty with rational numbers are any real number which can be written in the form P by Q, where yeah, P and Q are integers. So if a number can be written in this form, this is a rational number. Now √2 is not a rational number. So is 2 √2 plus 9, is this a rational number? Anybody?
No, it's not.
No, it's not. So this does not belong to Q. And in general, AU plus BV, if you take, it will not, that's why we can say that it will not belong to the set of rational numbers. So since the closure condition is violated, so the closure under linear combination is violated, so the answer to this question is no. Q is not a vector space over R, but as you rightly mentioned, that since a vector space So since a field is a scalar vector space over itself, so Q is a vector space over. Let me. So this is true, and I think it would be a good exercise to check that all the conditions are getting satisfied. Okay, so I am giving you these examples just to kind of familiarize you with different types of vector spaces. And okay, and before I move on to basis vectors, I would just like to mention that last day we talked about inner products, and inner products, just like vector space has this certain list of rules, inner products also have certain rules. And so inner products also follow certain rules. And I won't be discussing it here, but you can refer to R. Shankar, Principles of Quantum Mechanics, that book that I recommended a bit earlier. And okay, now that we are somewhat familiar, okay, I think I should stop at this point and ask you if there are any queries or questions, or whether you understood the examples that I presented to you. So I'll wait for 2 minutes. If there is any questions, then
Hi, can I ask a quick question?
sure, yes.
So, can you please go to the definition of vector space?
Sure.
Right. So,
Yeah.
the first one, yes, closure under linear combination. So you have A times V and A times U and B times V belonging to the space. But in principle, can't you have a condition where A times U can take your vector out of the space, and then adding B times V will bring it back again to the space? So shouldn't we have an elementary condition before this U plus V should, I mean, the unscaled multiplication should belong to the space before
Yes.
defining
So
combination?
basically, what you're saying is that this condition can be broken down into two parts. So you can say U plus V should belong to V, and AU should also belong to V.
Yeah,
Now the thing
not
is that
just breaking down. My question here is, isn't it absolute requirement? Not, not just
huh,
looking at it as breaking down, but it's more.
yeah, right. So basically, can we not? So should we not have these two conditions instead of this condition? So basically, if you look at it, what is U plus V belongs to V? It is the special case when A equal to 1 and B equal to 1. And what is AU belongs to V? When the special case when B equal to 0. So AU plus BV is actually encompassing these two conditions. So basically, yeah, one could in principle write closure under addition and multiplication, and linear combination would follow from it. But in another way, you can also argue that linear combination is kind of combining both the closure conditions.
Okay. No, so again, I think I'm a bit lost here, because I could think of a scenario where AU can take me out of the space and BU can bring me back again to the space. And if I cannot claim it will always belong to V, right?
Yes. But you are choosing a particular A and particular B. I am saying that this should hold for all A, all B, all U, all V. So if you take that general condition, because see, I can tailor made or hand pick a particular A, hand pick a particular B, but it won't be true for all the scenarios. Okay. Let me try to come up with an example. Okay, let's go here. So let's say you have so let's go back to our friend R3, and let's say you have some R1 vector, which is say some 1, 1, 1, and you have some R2 vector, which is 2, 2, 2. And you are saying that, okay, if I take A equal to 2 and B equal to -1, then let's say, okay, this is probably not a good example. Okay. So take it out of the space and bringing it back. So, okay, let's suppose that I have chosen the field to be complex numbers. So, of course, that cannot be the case for R3 as we have seen under closure. But let's say we are trying to find out whether it is a field over complex numbers. And we have chosen A equal to 2i, and we have chosen B equal to, say, -i. I think, yeah. And then you can do AR1 vector plus BR2 vector, and that would give you theta, which is a member of R3. That is what you are saying. But
Something like that.
I don't have to choose A equal to 2i and B equal to -i. I have to check with every A and every B. So for example, if I take instead of -i, if I take -2i, then I would get a complex vector. It will not be belonging to R3. So you have to check for all AB belonging to the field and all UV belonging to the vector space. Is that clear?
Yeah.
So okay. So basically, yeah, what you are saying is also correct. You can also define this as two independent conditions, U plus V belongs to V, AU belongs to V. I just did this because like linear combination is somewhat important in quantum mechanics, and also this encompasses both the conditions, uh, so to speak. So you can define it either way. It really is the same thing.
Okay. Thank you.
Okay, any other questions on the examples that we discussed? I mean, you guys are free to write in the chat as well. Well, of course, I don't really have the YouTube chat in front of me, but in the Zoom chat, you can write. Okay, maybe I'll take this time to ask you guys how many of you are like doing abstract algebra or something like vector spaces for the first time. Okay. Hmm. Okay, then I think there are no questions, and let's move on, I guess. All right, so now we will look at a very important concept related to vector spaces, and that is the concept of basis vectors and basis sets. Okay, now let's look at it in a general terms. So let's look at R3 only. And let's go back to our bracket notations, even in R3. So just so that we don't forget. So we have this X, Y, Z coordinates, and these are, say, the unit vectors. So basically X, Y, and Z have norms 1. Now, I'd like to ask you the question. whether using, say, only x and y, can you go to any point in R3? That's the question. Anybody? So when I say using x and y, I mean, can you take a linear combination of x and y and find any vector in R3?
No, we can't.
So basically, you can't go beyond the xy plane. For example, if you want to go to, say, this vector 3x 4y 5z, you can't, because you need this z ket vector in order to get there. So yeah, you can't do that. And but if I give you all of, say, if I repeat the same question with if I extend this set to include z ket also, now can you go to any point in R3?
Because 3D, so can
Uh-huh.
in X.
Hello. Uh, yes, audio input I think is a bit noisy. Can you write in the chat if possible? YouTube or Zoom, anything works. Actually, we can't hear you. So whoever has their mic on, can they please mute it? Because we can't really hear them and there's just a noise coming. Okay, I had to mute Manash Kumar Jha, I think, because uh, he was not really audible. And okay, so you can ask your questions in, or if you want to say something, you can do that in chat if your audio input is not working properly. Okay. So we were back to this question. Okay, can you go now with this modified like set using all three of x, y, z, can you go to any point in R3? Well, of course, yes, you can. Now, now let's. So this was really trivial. Now let's ask another similar question. So the question is that now I modify it further. I write, say, x plus y, x minus 2y, and z. So using this set, x plus y, x minus 2y, and z, now can you go to any point in R3? So you have to take a linear combination. So basically multiply each of this by scalars and add them.
Yes, we can go.
Right. Okay. So let's see how we can go. So let's try to take a general point in R3. So what would that look like? Say x1, y1, z1. So that would be a general point in R3. And remember, now we are using the column vector notation. So this is the same as saying, let's say x1 x hat plus y1 y hat and z1 z hat. Okay. So we want to go to this vector using this vectors that we have. So let's try to calculate what these vectors are like in terms of column matrices. So x, remember, is just 1 0 0, y is 0 1 0, and z is just 0 0 1. And so we have some x plus, so the three vectors that we have taken are x plus y. This is the first vector. So that would be, if you add this to column matrices, 1 1 0, and then if you take x minus 2y, then that would be something like 1 minus 2 0, and of course the other one is just z, and that is 0 0 1. Now, I want to take a linear combination of these three to get to our x1, y1, z1, which is a general vector. So if we take x1 to be any real number, y1 to be any real number, z1 to be any real number, x1, y1, z1 is one vector, is any vector in R3. Okay, now let's say we have to take a linear combination. So ax plus y. So basically, as I said, linear combination is just taking the vectors, multiplying them by some numbers, and then just adding them. So it would be something like this. And we want this to be our x1, y1, z1. So now if we write this in terms of column matrices, this would be like 1 1 0, B would be like 1 minus 2 0, and C would be like 0 0 1, and this would give me x1 y1 z1. And so if we just match the corresponding elements of the matrix, what we will find is that the first element would be on the left hand side would be just a into 1 plus b into 1. So a plus b, that would be on the right hand side x1, and here a into 1 plus b into minus 2, so a minus 2b will be y1, and c will of course be just z1, because just c into 1, and here everything is 0, and you have z1 on this side. Okay, now if you just solve this too, then you will just get a 2x1 plus y1 by 3, and b is x1 minus y1 by 3. So we can say that if just by putting the coefficients like this, we can go to any vector space, sorry, any point in the vector space R3. Okay, so indeed, using this set, we can go to any point. Now, the last question I promise regarding this that I will ask is that, and then I'll go on to define basis vectors. Oh, sorry, is that, oh, maybe not this. Maybe let's copy this. Okay. So now if I add I'm taking this set now. So now I have a set with 4 elements: xket, yket, zket, and xket plus yket. So with these 4 elements, can I go to any point in R3?
I think we can.
Yes, yes, of course you can, because just by x, y, z, you could go to any point. Now, if I add some extra element, then yes, even then you can, right? Because I'm not taking away anything, I'm adding one more. So, but now what is the problem? If I just want to express every vector in terms of these 4 vectors, let's say, let's maybe take an example here for that. So let's take this. Let's take this vector, which is 3, 4, 5, for example. Now you can represent it as 3x plus 4y plus 5z, and that is using only the first 3 elements, and you don't use this one altogether. But now I can also write it in some other way. For example, I can write it as say 3x plus y and then y plus 5z. So in this case, I have just used these 3, so x plus y, y and z, and I have not used x. So you can see that the problem is in taking an extra one more vector than what we really need, is that the representation is not unique. Okay, now we will try to define basis, what is a basis formally, and we will try to say which of these examples that we have taken actually forms a basis. So it's a basis set, or sometimes we just call it simply a basis. So a set P of vectors in a vector space, say V, is said to be a basis if every element of V can be written as a unique linear combination of the elements of E. So basically, if I have certain elements in the basis set, so some vectors say B1, B2 up to Bn. And these are the vectors, and we have some scalars also, which are members of the field. Then okay, so let me write it down. So by varying A1, just the field elements, and keeping the same, these are the basis set. So if this is the basis set, then so B1, B2, Bn are fixed. Just by varying A1, A2, and up to An, can you go to any vector in the vector space? If you can, then it is a basis. And another condition is that it has to be a unique linear combination. So in this example, for example, this was not a unique linear combination. There were two ways by which we could write this. So this set is not a basis. And what else example did we take? So yeah, so using this, we could write everything in our space. So this is a basis. And it was unique also. The representation was unique, as in A and B were like fixed for a given x1, y1, z1. A and B, A, B, C are fixed. The coefficients are fixed. So it was a unique representation. And of course, this is also a basis because, again, unique representation, and you can go to every point. Using this, you can't go to every point really. So this is not a basis. Okay, so that's what basis set or basis is. Now, we can have different types of bases. For example, let's look at the basis that we just discussed, which was x, y, z. So here, this basis, in this basis, x, y, and z, they're all orthogonal to each other. They're all perpendicular to each other. But now what if I look at the basis, the other basis that we considered here? So basically this one, if we look at, so if we consider this basis, then are all the elements orthogonal to each other? So let's check that. So we had, remember, so x plus y we calculated is 110. So let's call it, say, phi 0. And let's call phi 1 x minus 2y. And that is 1 minus 2, 0. Now, how do you know if two vectors are orthogonal or not? So you just have to take the inner product. Well, in the real space, that is equal to the same as the dot product. So this would be like 1, 1, 0 and 1 minus 2, 0. So this would be minus 1. So not 0. That means phi naught and phi 1 are not orthogonal. So there can be bases where elements are orthogonal to each other. There can be bases where they are not orthogonal to each other. Also, if you see here, all the vectors are unit vectors. That is norm of x, norm of y, and norm of z is 1 in this basis. But if you look at phi naught and phi 1, for example, then norm of phi naught is not 1. So this is basically root 2, because root over of 1 square plus 1 square. So root 2, and norm of phi 1 is root 5. So they might not be unit vectors, or in other words, they might not be normalized. For example, we have in this case, but here they are orthogonal and they are normalized, as in their norm is already 1, but here the norm is not 1. Of course, we can, if we have a basis, we can make the norm 1. So for example, if you have phi naught, a ket vector, and if you want to make its norm 1, what would you do? Just divide by the norm, right? That will make the norm 1. So for example, in this case, phi naught is just x plus y, and ket x plus ket y, and norm of phi naught is root 2. So like that, and phi 1 is x minus 2y and by root 5. Because norm of phi 1 is root 5, and of course z was already norm 1, we don't have to do anything to it, so z. So we have thus normalized the basis vector. So this process is called normalization, or making the norm 1. And this is something we would be having to do repeatedly in quantum mechanics, so or in quantum computation also. So this is something very important. All right. Now, so as I said that there are, as I showed that there are different types of bases. Different bases can have different properties. So we give special names to have those bases which have these special properties. For example, if elements of the basis B are orthogonal to each other, then we will call it an orthogonal basis. And if the elements of B are unit vectors or normalized, then we will call it a normalized basis. But suppose there's a basis which satisfies both the conditions. So elements are orthogonal to each other and elements of B are normalized, then we call it an orthonormal basis. Okay, so this is just a nomenclature. So as you can see that x, y, z. So this is here every vector is a unit vector or norm 1, and they are orthogonal. So this is an orthonormal basis. Okay, and this basis, we normalized this basis, made the norm of every one. So this is a normalized basis, but this is not orthogonal. So normalized basis. All right. And so if the basis is orthonormal, then you can see that if like if say B is this basis psi 1, psi 2 up to psi n, if this is the basis, then and if it is an orthonormal basis, then if I and j are not equal, then psi I psi j, that is the inner product, would be 0 if I is not equal to j. And since this is normalized, we can also say that mod psi I would be 1, but mod psi I we know is just root over of psi I psi I. So if you just square both sides, then psi I is 1. So it's 1 if I equal to j. And there's a notation for convenient notation for writing this is that psi j is delta ij. So delta ij is basically Kronecker delta function. So these are the conditions for orthonormal basis. And Kronecker delta function is exactly what we have written here. It's 0 if I not equal to j, it's 1 if I equal to j. So basically it is a useful notation, and in calculations it becomes very useful. So it's a good notation to know. Okay, so maybe I'll stop here if there are any problems or doubts.
Hello.
Yes.
In vector space, the use the set of vector over field, right? Definition in definition.
I
De-
can't really hear you well.
In definition of vector space, you say set of vector over field.
Yeah. So in the definition of vector space, wait,
Then,
yeah, so
then,
it's a vector space over field. Yes.
then can you give me the example of field in real application?
Field in real applications, a field, for example, they are the set of real numbers. That is a field. Or C, the set of complex numbers. That is a field. And field, remember what I said is that a set of scalars. Like if, for example, in R3, so maybe I should have been a bit more clear with that. So in R3, you have vectors which generally look like this, right? X1, Y1, Z, something like this. Now, what would you multiply? Like this is the vector of this vector space. But when you are doing different calculations, you are multiplying the vector by some numbers, right? Which we call scalars. So scalars is, so basically a field is a set which contains the scalars. So field is just a set of scalars. Now for different vector space, the scalars will be different. For example, for R3, the scalars are real numbers. So the field was real number, this field of real numbers. But for, as I had shown in an example, okay, if you take if this is your vector space, then you cannot multiply it with any, so Q is basically rational numbers. So you cannot multiply it with any. So let's say I have a vector here, which is V. You cannot multiply V with any scalar A. So it has to be rational again. So the scalars here are only rational. So it depends on the field, what scalars you can multiply it with, and the set of all the scalars that you can multiply a vector with is known as the field. Is that clear?
Yes, but any physical example?
Physical example. Okay. Uh,
I think fields are abstract in the sense they help diagnose the properties of vectors, which are in then can be used as physical objects. I don't think there are direct physical applications for fields.
Yes. I think you're right. Yeah,
They are passive objects, right? They are abstract to diagnose the properties, and once the properties of vectors are found, you can use them in physical applications.
True. Yes, that's exactly right. And so basically, fields, vector spaces, groups. So basically, there are many abstract mathematical structures. So basically, just like we defined vector spaces to be following some set of rules. So every abstract mathematical structure has a set of rules which are assigned to it, that if the members of a certain structure follows those rules, then we will call it a field or a group or a vector space. So these concepts are mainly abstract. Yeah, vector spaces we can motivate physically with, say, the real vector space and everything, but field I really don't know. Maybe there is some motivation, maybe there is, but um, I don't know actually. So even if there is, so, or maybe there isn't, we don't know. Okay, any other questions? Okay, so let's move on then. And now we are back to the good parts. So let's write down the first rule or first postulate of quantum mechanics. So quantum mechanics, so there are certain postulates which we assume to be true, and it has been found that assuming those postulates, you can explain all experimental results. And since they're postulates, as in they're some kind of axiom, so we assume that they are true. We don't question why are they true, or like of course we can justify why they are there in the first place, but we can't really question why on these basic postulates, on these basic principles. And this postulate one I had like very briefly mentioned in last class about the vectors in abstract vector space. So let's put it down a bit more formally now. So if you have a system, if you have a system, quantum mechanical system S, so let's write that down. So for every quantum mechanical system S, you define a complex Hilbert space. So there is a complex Hilbert space. And we'll denote it by H of S, S standing for the fact that it is for system S. And this is known as the state space of the system. Okay, now we have a new term here, which is the Hilbert space. So complex Hilbert space. So let's break that down. So what is a Hilbert space? So Hilbert space is a special kind of vector space, and it has an inner product defined on it. And it satisfies another condition which is known as Cauchy completeness. Okay, so vector space we have already learned, inner product we have learned. Now, what is this Cauchy completeness here? So, in order to understand Cauchy completeness, we need to understand something called the Cauchy sequence. Sorry. So a Cauchy sequence is a sequence for a vector space. It's just a sequence of vectors. Let's say V1, V2, V3, and so on up to Vn. It's a sequence, so the order matters. It's not a set. So order matters here. So if you can construct a sequence like, so Cauchy sequence is just a sequence like this, where distance between the elements keep on decreasing. That means the distance between V1 and V2 is more than the distance between V2 and V3, more than the distance between V3 and V4, and so on. So in other words, the distance of between Vi plus 1 and Vi is less than the distance between Vi and Vi minus 1. So let's say I equal to 1, then distance between V1 and V2, that is more than the distance between V2 and V3. So distance between V2 and V3 will be less. V4 will be even closer to V3 than V2 was, and so on. So this is a Cauchy sequence. Now, how do we describe distance in a vector space? So distance between, say, some Vi and Vj. So we do it just with the help of the norm. So norm of Vi ket minus Vj ket. So maybe I'll do it by a different color, the norm, so that it's clear. Yeah. So that's how we would describe the distance between two vectors in the vector space. Now, Cauchy completeness means that this means that the limit exists in V, as in the limit of the sequence. And what does the limit of the sequence means? Limit of sequence is Vn n tends to infinity. So that if that belongs to V, then V is said to be, so if limit of sequence of every Cauchy sequence that if it is in the same space, then we say that V is Cauchy complete. Okay, now this seems to be a very abstract definition. So let's look at real or some an example of a vector space, and let's see if it is Cauchy complete or not. I think that will be more useful. So let's take the vector space of the rational numbers over the field of rational numbers. Okay, so we had discussed before that this is indeed a vector space. And let's take a sequence Q0, Q1, Q2, like that, and so on up to potentially infinity. So what does it mean? So we have the number line, and the rational numbers are part of the number line, right? So there would be points on the number line here. So let's say we start with Q0, the first element of the sequence, and then we have Q1, and then progressively they will get closer. So Q2, Q3 will be even closer, Q4 will be even closer. So it will become very dense eventually. Basically, the distance between Q0 and Q1 would be greater than the distance between Q1 and Q2, and so on. So, but these are all rational numbers. Now notice that there are also a lot of irrational numbers between the rational numbers. So in fact, infinitely many irrational numbers between rational numbers. Between any two rational numbers. So it is entirely possible that if we keep on constructing this sequence, it might, in the limit n tends to infinity, it might go to some irrational number. So we will look at that with the help of an example. So let's say we take the following updation rule for our sequence. So qi plus 1 equal to half qi plus 2 by qi. Let's take this sequence. Now, let's start. So we have to take some starting point. So let's start with q not 1. Okay. So if you put I equal and q would be something like, so I'm not showing the calculation, it will be something like 17 by 12, which is 1.4166 and so on. So you can check this calculations. And
Maybe
q3 hello. Okay, so Q3 would be 1.4142, and all these are rational numbers also. What we need to check is that what happens if we take limit qi I tends to infinity. So let's suppose that this is w. Now let's take the limit on both sides of this equation. So limit qi plus 1 I tends to infinity will be half limit I tends to infinity qi plus 2 by qi. Now, if limit I tends to infinity qi is w, so of course, so basically you can also write it as q infinity. So qi plus 1 I tends to infinity will also tend to the same limiting value. So this would be w also, or q infinity. And half, so again limiting value is w for I and 2 by w, something like that. So let's try to solve it. So 2w, and here, so I'm taking 2 here, and it would be w squared plus 2 by w. That is 2w squared, w squared plus Okay, I'm sorry. I think I disconnected myself. Is it visible now?
Not yet.
Not yet. Okay, let me check. Almost. Okay, so am I audible, and also is my screen visible right now?
Yes, yes, it's okay.
Okay, okay. So how far did you follow and how much did you miss? Can anybody tell me?
Yes, yes, we are here.
You are here.
Yeah,
I'm asking that how much did you follow till this till the last point, w
yeah,
equal to
yeah,
root 2?
yeah.
Okay, okay, okay. Thanks.
Can you
Okay.
repeat that last point again?
Oh, sure. I'll do that. I'll do that.
Thank you.
Okay. So basically, what we were doing is that we had constructed a sequence of rational numbers, like at least we started with rational numbers, and we defined an updation rule like this, and we were trying to calculate the limit when of this sequence element when the I is infinity. So basically, the infinite, basically, yeah. So the limiting value of the sequence, in other words, because you can see that since the numbers are getting closer and closer to one another, you will have a q infinite here, which is a limiting point, and we were trying to calculate that. So we took the limit I tends to infinity on both sides of the updation rule, which we had here, and then since I tends to infinite qi is w, so of course this will also be w, because I tends to infinity, it's same limiting point. So we replace this by w, qi I tends to infinity again replaced by w, and we solved the quadratic equation, and we got w equal to root 2. And what I was asking at this point is that is root 2 a rational number or an irrational number?
Yes,
Right. So root 2 is an irrational number. So remember, we were working with the vector space of Q over Q. So the vector space of rational numbers over the field of rational numbers. But for this sequence, and we constructed a Cauchy sequence. So this sequence, the values were getting subsequently closer to one another. And we found that in the limit of this sequence, we find that it is going out of the set of rational numbers. So this does not belong to the set of rational numbers, right? So that means since the limiting point of the Cauchy sequence does not, so there is one Cauchy sequence at least, which is this Cauchy sequence, where the limiting point does not lie inside the set of rational numbers. We can say that Q over Q, this vector space, is not Cauchy complete. So remember what was the definition of Cauchy completeness? That the limit of every Cauchy sequence should lie in the same vector space. But here, the limit of at least one Cauchy sequence is not lying in the same vector space. So now this was all mathematical. Now, how do we understand this physically? So the reason why it did not converge in the same, there is a Cauchy sequence which does not converge in the same Q set, is that the set of irrational numbers has holes in them. As in, since as we mentioned that there are infinitely many irrational numbers between any two rational numbers. So between any of these 2 points, there are many points which are missing from the set of rational numbers. So basically there are gaps or holes in the set of, so very loosely speaking, we can say that so there are gaps or holes in the set of rational numbers. And that is why it was not Cauchy complete. So when we say that it will be Cauchy complete, that then in this sense, there will be no gaps or holes in the set. For example, if you take the set of real numbers, for example, or the set of complex numbers, for example, there will be no gaps or holes. So, for example, R3, the set of R3 on R will be a Hilbert space because it will be Cauchy complete. Or rather, let's deal with Cauchy completeness only right now. So it will be Cauchy complete. Or the C2 on C. These vector spaces would be Cauchy complete. Okay, and since they already have their vector spaces already with a inner product defined on them, they will also be Hilbert spaces. So is the concept of Cauchy completeness okay for you guys? Is it clear?
Yes, but could you also direct us to any resource particularly explaining more about Cauchy completeness? Because I think this is a very good explanation and I haven't found any similar to this before.
Okay, actually, I also didn't find it in any particular textbooks. Like over the years, I think Cauchy completeness you can find in some real analysis textbooks, if I'm not wrong. But okay, I'll look at any resources which are available and I'll share it with you maybe in the next session.
Absolutely. Thank you so much.
Okay, 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 okay. All right. So, any other questions about Cauchy completeness? Okay, I think I missed a few chats in the pending.
Hello.
Yeah, yeah.
I have a question. What is the
Yeah.
role of this Cauchy sequence in this Hilbert space?
Yeah, the role, so there's no role as such. So basically, the fact that the Hilbert space is Cauchy complete ensures that the formalism of quantum mechanics works well. So yeah, there's no such role. So basically, it just ensures that there are no holes or gaps in the space, because then it would be difficult to do things to establish the formalism of quantum mechanics as we will try to do now. So yeah, there's not really role of Cauchy completeness as such, apart from ensuring that there are no holes in this space.
So we have a vector
Yes.
space. We bestow. Oh, sorry. Did I interrupt a
Yeah,
question?
yes. Okay, I think you can go first and then we can have the next question.
All right. So we have vector spaces and then we associate inner products to them, then that become inner product space, and then we add
Right.
one more constraint to it, Cauchy completeness, and that becomes Hilbert
Right.
space, is it?
Exactly. For example, if you see Q over Q, that is a vector space and you can define an inner product on it, very similar to the way you define inner product in a real space, for example. But that is, so it is an inner product space, but it is not Cauchy complete, so we cannot call it a Hilbert space. Yes, you are absolutely right. That
So
Cauchy
Hilbert
completeness.
space is a vector space with inner product and Cauchy completeness defined, right?
Exactly. Yeah. So I think, yeah, I defined that here. It is a vector space with an inner product and plus Cauchy completeness.
Okay, thank you.
Okay. So I think there
Hello.
was another question which was coming up. Yeah, go ahead.
I learned about Hilbert space before, and that
Uh-huh.
possesses some special property, right? But why so special Hilbert space in quantum mechanics?
Why Hilbert space is so special in quantum mechanics? Well, as we shall see in the next postulate, that all the states of the system we will define as vectors in this Hilbert space. And so since all the states are residing in the Hilbert space, so that's why it's quite important. Okay, now if you're asking why we did not define, why are we sticking with Hilbert space? We could have defined some other kinds of space. I guess I can't give the justification to you right now, but since it's a postulate, we generally don't question why. Why Hilbert space, why not some other space, but I'm sure there is some justification, but I really don't know what that justification is. But what can I tell you is that if we assume that for every system there is a Hilbert space, then if we lay down the other postulates, then we can say that all the experimental results are derived from those basic set of rules, and this is one of those rules that we are laying down. Yeah, but for sure, there might be some justification that I'm not aware of.
Yes.
I'm sorry, I could not really answer your question on this one. Okay, so any other questions?
No, thank you.
Hello, I have a small doubt that you
Yeah.
previously said that there should be no holes. So here holes represented what? I mean, what
Yeah,
is
holes
actually
in some sense a discontinuity in the space. For example, in the set of rational numbers or in the vector space of rational numbers, for example. So there are some irrational numbers missing in between, right? So that makes the space discontinuous. So in that sense, very loosely, we can say that If space is not Cauchy complete, then there are holes in them, and if it is Cauchy complete, there are no holes in them. So this is kind of an intuitive way of understanding this. So is that clear?
Yeah, yes.
Okay, so basically you can say that there are holes or gaps in the Cauchy sense of the term, in the Cauchy sequence sense of the term, as in with this definition that the limit of the Cauchy sequence is going out of the space. So if the limit is going out of the space, then there's certainly some gaps or some elements which are missing from that space. And in fact, I think in real analysis, there's something where you actually fill in these gaps. So you take the set of rational numbers, you fill in the gaps, and you get the set of real numbers. So do you understand what I mean? So okay, is that clear?
Yes.
Okay, sure. So I think I missed some questions in the chat. I don't know why I couldn't see them before. So Rajrupa had asked, do non-orthogonal basis has physical significance, or in other way, can we use non-orthogonal basis in physical system to represent a vector? Non-orthogonal basis don't have any physical significance as such, as far as I'm aware. But yes, you can always use non-orthogonal basis in a physical system to represent a vector. But that would make things a little bit complicated. Representing that in non-orthogonal basis is, in general, not very convenient, and that's why we always try to represent in bases which are orthonormal, as in they're orthogonal and also normalized. So does that answer your question? Rajrupa, if you're still there. Okay, I hope she was still there, and I hope it answered her question. Okay, so I think we are out of time today. I wanted to do some more things, but all right. So at least we have been able to establish what a Hilbert space is. So maybe next day we will continue with this first postulate and go on to the the other four postulates of quantum mechanics, and hopefully next class we will be able to discuss them all. If you had any other queries over the course of this second session of the QIQT tutorials, so I would be there for some time. We can discuss now. And I understand if today's session was a bit too mathematical, but I wanted to be a little bit rigorous with vector spaces because everything is dependent on that, and one has to understand that really well. So over the course of this session, I have asked you to do some things at home. For example, um, proving that certain spaces, certain sets are Hilbert spaces or they are not Hilbert spaces. For example, this, and to prove that the set of rational numbers is a vector space over itself. And I think one more. Yeah, whether if C2 is a vector space over C. So I would ask you to do that, and maybe I'll also post the solutions before the last class, maybe email you the solutions. In the meantime, if you have any questions or queries, feel free. And I am sorry that I missed some of the things in chat. I thought I had the chat open in front of me, but somehow, yeah, I missed them, but okay. Also, if you are having some suggestions, you can say like if it is being too slow or too fast or too detailed or not so detailed. If you have any thoughts on or any suggestions about how it should go forward, you can also share that with us. Sure. After the class, okay. Maybe if you give me some time, maybe not immediately after the class. Yeah. So, yeah, sure. I'll provide you notes on the specific topic, or I'll mention which maybe the chapters, specific chapters from certain books that you can read up in order to understand those things better. Yeah, sure, I can do that. And yes, I'll also find out any notes or papers if I can. Yeah, I think Yeah, I'll try to find something like that, and I'll try to send it to like send it to the entire group basically by email. Like Cauchy completeness, so the explanation that I have given you is something that I have come up with over the years, piecing together different pieces of information, putting together. So yeah, so I'll try to see if there's anything where it is um, explained rigorously and in a better way. Yes, and a lot of you had actually answered when I had asked you the questions. You had answered in the chat, but for some reason I was not able to see them, so I'm sorry. So yeah, so next day onwards, I hope that we next class is when? Okay, next class. So basically, we will have another set of tutorials given by a colleague of mine, Shomit Mukherjee. So it will be tomorrow. It will be tomorrow, 3 to 5. So Sunday, 3 to 5 will be his tutorial. And I'll take the next tutorial on Wednesday. And so I'll be taking tutorials on Wednesdays and Saturdays for the time being. Okay, I think there are no more questions or anything. Okay, so that's it for today. See you on Wednesday again, and also please attend tomorrow's tutorial. It will be on ontological models. So basically an introduction to, so it's a prequel to Bell inequalities and Bell non-locality. So it would be taken by Shobit Mukherjee. So please do attend that if you can. It would be from 3 to 5 p.m. tomorrow. Okay, so with that, I'll leave and see you all.